Okay, so welcome back, and now we're going to do a couple of examples. So we're going to be given this series, and let's, for the first part, calculate S10 and estimate the error, okay? So that's going to be the remainder part, right? So we know, well, first of all, let's calculate S10. So S10 is equal to the summation of n equals 1 to 10 of 1 over n cubed. And so that's going to equal 1 over 1, right? Plus 1 over 8 plus 1 over 27 plus 1 over 64. Right? And if we keep going, what do we get? We get 1 over 125, and then all the way up to 1 over, what is it? 1 over 1,000. Right, so we could use our calculator to do this. Okay. Now keep in mind, even though in my class I don't allow calculators and everything here needs to be an exact exact form, there are certain things that it's obviously you're going to have to use a calculator. Things like estimate errors and things like that, you're going to have to use a calculator. So again, just make sure you read the directions carefully. But normally you're going to have to use a calculator for something like this to estimate the partial sum. So now in this case, if you do use a calculator, what do you get? You get approximately equal to, what do I have here? Where is it? 1.1973. Oh, 753. Okay, so now there's the partial sum. Okay, now we want to estimate the error. Okay, now remember the error, so the remainder error, we know that S of 10 is going to be less than what? Well, the improper integral from 10 to infinity of 1 over, oh, oops, not n. 1 over x cubed dx. Okay, and so what is this equal to? Well, this is equal to the limit as t approaches infinity of the integral from 10 to t of 1 over x cubed dx. And of course, this is going to equal the limit as t approaches infinity of what? This is going to be negative 1 over 2x squared, evaluated from 10 to t, right? And so then what? Now we're going to evaluate this. Okay, so I'm going to say this is equal to, oh, there's no integral. It's going to be the limit as t approaches infinity. And then this is going to become what? The negative, and it's going to be 1 over 2t squared minus 1 over 2 10 squared. Okay, and then using the property of limits, and I'm going to distribute the negative sign. So what do we get? We get 1 over 200 right? 1 over 200 minus the limit as t approaches infinity of 1 over 2t squared. Okay, so all I did was use the property of limits, and this is, if I distribute the negative sign, I switch these, right? It just switches the subtraction. And then, of course, this is a constant, so I don't need the limit there. So the limit goes on this one. So as t goes to infinity, this is going to 0. Right? So that's going to 0. And so we know that 1 over 200, right? Okay. Oh, hold on. Look why I wrote that. This is arsenal. Sorry. Okay. So now, what do we know? We know that error has to be less than 1 over 200 or 0.005, right? So this is, so we know that the error for this is r sub 10 and has to be less than 0.005. Now, in general, okay, so in general, instead of using 10, we could use capital N. And so we can get a formula that represents the remainder error. Okay, so instead of using 10 here, we could solve this thing for just capital N, and what would happen? Well, what we would get is if you went through the same process, instead of having 10, you just had capital N, what you would do is you would get the formula r sub n is less than what? Well, in this case, you end up with 1 over 2, so you end up with 1 over 2 n capital N squared. So now you know for any n value, the remainder has to be less than this. Okay, so now you can basically calculate the remainder error for any n, okay, by using this formula. Okay, so in this case it's 0.005. Okay, now in the next part, part B, it asks, okay, well, we want to find n such that we can estimate the series to within 0.001. Okay, so again, we want to find out the least value of capital N necessary such that the partial sum will estimate the series of 1 over n cubed to within 0.001. Okay, so what does that mean? Well, let's look at it. in this case, we want to find, so in B, this is B, we want to find n such that r sub n is less than 0.001, right? Okay, so that's what we're doing. But now, we know that r sub n, based on this series, r sub n is less than 1 over 2n squared, right? So basically we want this to equal 0.001. That makes sense, right? Okay. So if we know that r sub n is less than this, right, and we want to be less than 0.001, then if we solve for this, then we'll be fine. We could solve for equal to, and then that would be fine too, and realize that we would have to round up, and we're going to have to round up here anyway, but let's find out what this turns out to be. Let me make sure I got the right number here. Yeah, okay, 0.001. Okay, so now let's solve for this inequality. So now all we do is we're going to invert or take the reciprocal of both sides. So that means this is going to be 2n squared is greater than what? 1 over 0.001. Which is, if we want to rewrite this 0.001 is what? 1 over 1,000, right? So if we take the reciprocal of both sides, then we get 1,000. So same thing, okay? So now I'm going to divide both sides by 2. If I divide both sides by 2, I get n squared is greater than 500. And if I take the square root of both sides, and again, n is positive, so we're only going to deal with the positive value of the square root. So n is going to be greater than the square root of 500, which gives us what? Well, this is going to equal what? 25 times 4, or 100 times 5, right? So this is going to end up being 10 times the square root of 5. So again, we have to use our calculator because we're trying to find the minimum value of n, and n is an integer, okay? And so what do we get? Well, let's find out. So we get so we get 22.36, Okay, 22.36. Okay, so but now what it says is n has to be bigger than that. So what's the minimum integer that's bigger than that? Well, 23. So n has to equal at least 23. And that's it. Have a great day.